Hello students, welcome to physics class. Today we discuss the torque experienced for a current carrying coil in a uniform magnetic field. Consider we are placing a coil PQRS in a uniform magnetic field. PQRS is a rectangular coil, the side A and B. I current is passing through this rectangular coil in this direction from P, Q, Q to R to S, and S to P. You can say in clockwise direction. A current I is flowing through this rectangular coil, which is placed in a uniform magnetic field. Now this rectangular coil, this is the axis of this rectangular coil, an axis which is passing through the center of this rectangular coil. Say I current is flowing through this rectangular coil. A and B are the sides of this rectangular coil. So A into B, length into breadth, that is capital A, is the area of the rectangular coil. Now this rectangular coil makes an angle theta with the magnetic field. That is, the normal to this rectangular coil makes an angle theta with the direction of magnetic field. Angle theta is the angle between the normal to the plane of this loop and the magnetic field. Now we want to find what is the magnitude of force acting on the rectangular coil. First we see the side QR and PS. The length of the side QR and PS is A. First QR, side QR, the current is from Q to R. Apply Fleming's left hand rule to find the direction of force. By applying Fleming's left hand rule, you can see that the forefinger in the direction of magnetic field. This is the direction of magnetic field. Forefinger in the direction of magnetic field. And the middle finger in the direction of current. This is the direction of current. So the thumb point in the upward direction. So that is the force direction in the side QR. The force is acting in upward direction. Force is acting in upward direction. And what about the side PS? For the side PS, the current is just opposite of that one. Magnetic field is in the same direction. So if you are applying Fleming's left hand rule, first forefinger in the direction of magnetic field and the middle finger in the direction of current, the thumb come downward. So the force is just a downward direction. So the force on QR and PS are in opposite direction. The magnitude is the magnitude of side QR, the force on QR is equal to what? The strength of magnetic field into the length of the side. What is the length of the side? A into current I into angle between the magnetic field and the normal. Suppose it is theta, then we can say BAI sin theta. What about on the side PS? The side PS is equal to B into the same magnetic field, same length, same current, angle is also same. So the magnitude of force on QR and PS is same, but they are opposite in direction. So what happened? The force on QR and PS are cancel each other because they have same magnitude and opposite in direction. So they're getting cancel each other. But on the side PQ and RS, first find what is the direction of the side RS and PQ. What is the direction of force acting on the side RS and PQ? Apply Fleming's left hand rule. So on the side RS, the force is, the magnetic field is in this direction, in the direction of forefinger, middle finger in the direction of current, then the thumb point in the direction of current, the magnetic force. So actually that is coming out of this plane. That is force coming out of this plane, perpendicular to this plane of board and outward. So it's shown here, this is the direction of force. Then what about on the side PQ? The current gets reversed. So the direction of magnetic field is same, current is just opposite of that one. So what happened to this? Okay, the thumb point inward. That is perpendicular to this plane of board and inward. So that's why the direction is shown. The force is perpendicular to the plane of board and inward. Now the forces on the side PQ and RS are opposite in direction. The force on PQ is inward and force on RS is outward. Perpendicular to the plane, outward and inward. They are opposite in direction. But you see the line of action is different. The line of action is different. Let's find the magnitude. The force on PQ. The force on PQ. You can see that PQ and RS are perpendicular to the magnetic field actually. The magnetic field is from north to south. So the side PQ and RS are perpendicular to the magnetic field. So theta is equal to 90 degree. So what is the force on PQ? Force on PQ is equal to strength of magnetic field into current into the length of the side PQ. What is the length of the side is B. So BIB sine 90. Sine 90 is what? That's why BIB. That is normal and inward. Okay, normal and inward. That force is normal and inward. And force on RS. Force on RS. The magnetic field strength is B. And the current I. And the length is B. The same length and same current and same magnetic field. But the direction is opposite. That is normal and outward. But you see, the line of action of these two forces are different. Even though the magnitude is same, they are not cancel each other because the line of action is different. And so these two forces form a couple which produce a torque. Let's find the magnitude of torque. The torque is equal to the force into perpendicular distance. Torque is equal to force into perpendicular distance. What is force? Force is equal to BIB. Now we want to find the perpendicular distance. For that, suppose we are drawing the side QR here. The QR is shown here. Okay, the force on PQ is shown here at the end of PQ, that is on Q. The force F which is acting inward, and the force on RS is shown here at the end R, that is force outward. This is inward force and this is outward force. So two forces, the line of action is different, they are equal forces, so they produce a torque. We want to find what is the torque. We know torque is equal to force into perpendicular distance. This is the perpendicular distance between these two forces. What is that? This is the side A, and the angle between magnetic field and normal is theta. So this angle is also theta. So we can write this distance is A sine theta by using trigonometric relation. This distance is equal to A sine theta. So the perpendicular distance is equal to A sine theta. Substitute either of this force having a magnitude of BIB. So that is BIB into perpendicular distance A sine theta. That is BIB into A sine theta. Now instead of B into A, that is the length into breadth of this rectangle, can we write as area? B into A is equal to area. That is torque is equal to BIA into sine theta. What is theta? Angle between the normal and the magnetic field. At that instant, angle between the normal and the magnetic field direction. Okay. Suppose if the rectangular loop has n number of turns, instead of taking a single turns, if the rectangular loop having n number of turns, you can write the torque is equal to NBIA sine theta. Okay, the torque is equal to NBIA sine theta. Now rearrange this equation. First we are writing n and rearranging this I into A first, I into A, NIA into B sine theta. Now we introducing a term that current into area cross section. Current into area cross section of a loop. NIA. That is the magnetic moment of that loop. Magnetic moment. Suppose we have a circular coil like this way. I current is passing through the circular coil. it produces a magnetic field. The strength of this magnetic field, or the strength of this magnet, we can say it is a magnet because it can produce a magnetic field. So the strength of this magnet is measured by using a physical quantity known as magnetic moment. For a current carrying coil, the magnetic moment is taken as current into area cross section. Current into area cross section. That's the magnetic moment. We have n number of turns, we will write as Ni into A. That is the magnetic moment. And it is a vector quantity and its direction can be predicted by our right hand thumb rule. The direction of this magnetic moment is predicted by right hand thumb rule. In this case, hold your curved finger of the right hand in the direction of current and thumb point in the direction of magnetic moment. Here in this diagram, if this coil is placed in this plane and the current is in anti-clockwise direction, the magnetic moment is perpendicular to the plane of the board and outward. Similarly, if the current is in clockwise direction, we can see that the magnetic field or the magnetic moment is in perpendicular to the plane and inward. Hold your right hand, the curved finger in the direction of current and thumb point in the direction of magnetic moment. So we will discuss the concept of magnetic moment in the chapter magnetism in detail. Okay, now we consider Ni into A is taken as the magnetic moment of this rectangular coil. That's why we denote the symbol M, magnetic moment, M, Ni into A, magnetic moment, into B sine theta, into B sine theta. So in this case, the direction of magnetic moment is same in the direction of normal. Apply Fleming's apply right hand thumb rule. We can see the direction of magnetic moment is in the direction of normal to this plane. So the M into B sine theta, torque is equal to M into B sine theta. The angle between M and B is theta because M is in the direction of normal. Actually, we know theta is the angle between normal and magnetic field. You can say M and B, angle between M and B. So what is torque? Torque is equal to MB sine theta. Or we can write torque is in vector form. Torque is equal to M cross B. The direction of this torque in such a way that it rotates the loop clockwise about the axis of suspension. Because of this torque, this freely suspended coil will rotate in clockwise. You know that torque is always producing a rotating effect. So this rectangular coil is rotating in this magnetic field in clockwise direction. Suppose at any instant, if angle between the magnetic field and normal is equal to 0, that is theta is equal to 0, the angle between the direction of magnetic field and the normal to this plane is 0. Theta is equal to 0. The torque is equal to 0. That is, the plane of this coil is perpendicular to the magnetic field. If the plane is perpendicular to the magnetic field, the angle between the magnetic field and the normal is 0. So by the time torque is equal to 0. Now, if the plane is parallel to the magnetic field, the angle between normal and the magnetic field is 90. That is equal to theta equal to 90. Then we can say the torque is maximum. What the maximum torque is equal to MB into sine 90. Sine 90 is 1. So we can simply write M into B. M is equal to Ni into A. Nia into B. That's the maximum torque acting on this coil. The torque is maximum when the plane of this coil is parallel to the magnetic field. That angle between normal and the magnetic field is 90 degree. And if the plane is perpendicular to the magnetic field, angle between normal and the magnetic field is 0 by the time torque is equal to 0. In all other angle, if the angle between magnetic field and normal is theta, we can write torque is equal to MB sine theta or M cross B. Now let us find what is the force of interaction between two parallel current carrying conductors. In 1820, Ampere observed that the parallel current carrying conductors attract each other and anti-parallel current carrying conductors repel each other. Now let us find what is the magnitude of force of attraction and repulsion between the current carrying conductor. Here we have two current carrying conductor having infinite length. Say the length is not finite, the length is infinite length. We have two conductor A, B and C, D. Placed very close to each other. The distance between these two conductors is R. AB carrying a current I1 and CD having a current I2. Both current are in same direction. Now, suppose if you are considering the first conductor, that's AB, which produce a magnetic field at the site of CD. At any point of the conductor CD, the current in I1 produce a magnetic field. We can write this magnetic field at the point CD is equal to B1 is equal to mu 0 I1 by 2 pi r. We know what is the magnetic field produced by a straight line conductor. That is equal to mu 0 into current by 2 pi r. Here the current is I1. So mu 0 I1 by 2 pi r. Distance to the conductor CD is r. Mu 0 I1 by 2 pi r. Now what is the direction of B1? That can be predicted by that can be predicted by right hand thumb rule. If you are holding this conductor in such a way that thumb point in the direction of current, then all the curved finger give the direction of magnetic field. So at this point, the magnetic field is perpendicular to the plane of this board and inward. B1 is perpendicular to the plane of board and inward. The magnetic field strength is mu 0 I1 by 2 pi r. Now we can consider now this conductor CD is in a uniform magnetic field B1, in a perpendicular magnetic field B1. So it experiences a force. Let us calculate what is the force acting on CD for a length L. The force acting on length L of the wire CD is, that force is equal to, the equation force is equal to BIL sin theta. BIL sin theta. Here theta is 90 because the field is perpendicular to the plane of the board or perpendicular to the current. So angle theta is equal to 90 degree. So the force is equal to, you can write as force on second conductor, that's why F2 is equal to the current on second conductor, that is I2, into length. We are calculating force on a length L, that's why length L, into the strength of magnetic field. What is the magnetic field here? That is B1. That is B1. Into angle between the magnetic field and the direction of current is 90. So that sine 90. So substitute for B1. So I2 into L into B1 is mu 0 I1 by 2 pi r. Rearrange like this: mu 0 I1 I2 L by 2 pi r. As it have an infinite length, better calculate what is the force per unit length. So we are taking this L to left side, that is F2 by L. That is the force on a unit length of the wire CD is equal to F2 by L is equal to mu 0 I1 I2 by 2 pi r. Apply Fleming's left hand rule to find the direction of this force. So here the magnetic field inward, that is in the direction of forefinger, and this is the direction of current, and you can see the thumb is pointing towards AB. That is, this force F2 is acting towards AB. So the conductor CD, the force per unit length is mu 0 I1 I2 by 2 pi r, which is acting towards the conductor AB. So better we can say the conductor AB is attracting the CD with a force per unit length of mu 0 I1 I2 by 2 pi r. This conductor experience an attractive force, that is force per unit length mu 0 I1 I2 by 2 pi r. Similarly, we can say the conductor CD produce a magnetic field at any point of AB. That's equal to B2 is equal to mu 0 into current in CD. That's equal to I2 divided by 2 pi into distance to this point. Distance is r. So the magnetic field at any point of AB is equal to mu 0 I2 by 2 pi r. The direction, apply right hand thumb rule. The direction, if you are holding this conductor CD in our right hand, the curved finger coming out of this board. So the magnetic field is perpendicular to the plane and out. So that's the direction of B2 is shown here. Now we can say the conductor AB is in a uniform magnetic field B2, perpendicular magnetic field B2. So the force acting on the length L of the wire AB can be written as F1 is equal to current I1 into length L into B2 into sine 90. Substitute for B2 because the conductor AB is in the magnetic field of CT. Substitute for B2. B2 is equal to mu 0 I2 by 2 pi r. And rearrange it, mu 0 I1 I2 L divided by 2 pi r. As AB having infinite length, let's find what is the force per unit length. The force per unit length is, take the L to left side. So force by length is equal to mu 0 I1 I2 by 2 pi r. And its direction, again apply Fleming's left hand rule. So we can see the direction of magnetic field is coming outward, coming out of this plane of this board, and the current is in the upward direction. So what happened? The thumb point towards CT. That is, the force F1 is just opposite of force F2. It means the AB, the conductor AB is attracted towards CT with the same force per unit length. You see that both the force per unit length is same, mu 0 I1 I2 by 2 pi r. So we can conclude that if you are placing two current carrying conductor parallel to each other, if the current is in the same direction, they will attract with a force per unit length of mu 0 I1 I2 by 2 pi r. You can see the magnitude of force is equal, but they are opposite in direction. It means they attract each other. Parallel current carrying conductors attract each other. Or if the current is in opposite direction, they will repel each other. Then the conclusion, the parallel current attract each other and anti-parallel current carrying conductors repel each other. The magnitude of force per unit length is mu 0 I1 I2 by 2 pi r. Now suppose in this equation force per unit length mu 0 I1 I2 by 2 pi r, we are putting I1 I2. I1 is equal to I2 is equal to 1 ampere and R is equal to 1 meter. It means 1 ampere current is passing through this both conductor and they are separated by 1 meter. Then what is force per unit length between them? That's equal to, in this equation, I1 I2 equal to 1, R equal to 1, you getting mu 0 by 2 pi. The force per unit length between these two conductor is mu 0 by 2 pi. What is the value of mu 0? 4 pi into 10 raised to minus 7. Isn't it? So if you are dividing the force per unit length, F is equal to, you getting 2 into 10 raised to minus 7 Newton per meter. Now we can define the 1 ampere. Define 1 ampere. The 1 ampere is that value of steady current which on flowing in each of the two parallel infinitely long conductors of negligible cross section placed in vacuum at a distance 1 meter from each other produces between them a force of 2 into 10 raised to minus 7 Newton per meter of their length. That is the definition of 1 ampere in terms of force per unit length of two parallel current carrying conductor. Once more, if you are putting I1 is equal to I2 equal to 1 ampere and R equal to 1 meter, we getting the force per unit length between two parallel current carrying conductor become 2 into 10 raised to minus 7 Newton per meter. The current in both this conductor is 1 ampere. So we can define 1 ampere as 1 ampere is that value of steady current which on flowing in each of the two parallel infinitely long conductors of negligible cross section placed in vacuum at a distance 1 meter from each other produces between them a force 2 into 10 raised to minus 7 Newton per meter of their length. That's the definition of 1 ampere in terms of force per unit length between two parallel current carrying conductors. That's all today. Thank you.